study. So our speaker today is Roozbeh, who will speak about Bergman's calculus. Bergman's algebra.
Algebra.
Okay, please go ahead.
All right, thank you very much. It's lovely to be in Buenos Aires. So I'm going to talk about I really basically said it correct, not correctly. Or Bergman algebra.
Wait a second. Do you have the mic? You don't have the mic on
The mic, yes. Is it working? It is. You should tap the button.
No, it's working. Okay. All right. So the topic is Bergman algebras, and we are doing this. We are in the middle of it really with Huanhuan Li in Hefei and Raimund in Nanjing. So we are working still on it. Hopefully, we'll finish it soon. But let me just start with the algebra we all know and love, the Leavitt path algebras. So you start with the graph E, and then you associate an algebra to this graph. It's a directed graph. And the way you do this here, you look at these coefficients, you generate a free algebra, you pick up all the vertices, this is vertices, all the edges, and you allow yourself that you would be able to go back, so you get another copy of vertices.
The marker writes later at each letter. You start with the D and...
What do you mean?
The trace is... Can you see it, Gisela?
Is everybody can see this?
I can see it, but I want in the recording.
Okay. So yeah, so you have this graph, and the algebra you associate is you pick some field, this is fixed, and you get this free algebra. This is a non-unit of free algebra. Eventually, this E0 is going to play the role of the unit. And then you put here some relations. I'm not going to put these relations here at the moment, but some very nice relations. Okay, and this gives you an algebra, and as soon as you get a very particular graph, maybe this one, which has n loops, and you plug this into this machinery, and I'm going to call it Ln, what you get, let me call it also A, this ring, is the free algebra generated by two n symbols. Now, this time I have to emphasize, now this is a free unital algebra. So if you put into the machinery and work it out, and you want to express it this way, this is a free unital, free unital algebra. And the relations that you get is, you just look at this row, and you multiply it with this column, and you force this to be 1, and then you swap the position, and then again, you force that to be 1. So you just swap the position here. And this also has to be 1, but now if you multiply, it's an n by n matrix, so I force this to be identity of that matrix. Okay. Now, this was introduced by Leavitt in end of 50s, I guess, Leavitt. And he wanted, so this A, to have this property that A would be isomorphic with n copies of A. And you can prove this is a good undergrad exercise using these relations here, that A is n copies of A as A left or right module. That's very easy to prove once you can guess the maps. But what's much more difficult is that this is not the case, that A is isomorphic to spaces in the middle. So this is much more difficult. And he managed to prove that in the middle, there is no isomorphism between these spaces. The first time is that n-dimensional space is the same as this. So easy, I would say difficult. And then he proves, again, kind of element-wise, that this A is a simple, is non-zero, simple ring. Okay. So then it turned out this is a very, very interesting ring. A lot of very nice properties. It's very rich in structure. Even if you get the units of this ring, so elements which are invertible, although again from here you cannot see, you cannot really guess the invertible elements here. But the invertible elements of this contains the Thomson group. This is a very complicated group. But yeah, so it contains Thomson group. So that already tells you that this structure is very interesting. Okay, so that's one way to define Leavitt path algebras. You start with this graph and so generators and relations. There are other ways. One, I just very briefly tell you, is that you start with a groupoid. So this means a category which each morphism has an inverse. And then you put some nice topology, because what you want, you fix again this field, you get your groupoid, and you look at all the maps from this groupoid to this K. But because I want to multiply these functions, okay, I want to control the support of this. So this topology that you have controls the support. Mm-hmm.
Sorry. Markers are very nice. You want to try
The different one? Okay.
Yeah.
All right, so you start with, so this is again standard, you look at all these functions, but then the support, in the standard one, the support has to be finite. If the support is finite, then you can multiply. So if you have F star G, this is the multiplication you want to apply to 1 alpha. Well, the way you do in standard way is F of maybe gamma, G of beta, and this splits alpha. So this is your morphism alpha. And then you have beta and gamma, which gives you alpha. And then you plug this into here, and you get the sum. And then if there are a finite number of, because you just look at all these way that you can split alpha, you want to make sure that these numbers are finite. This sum makes sense. So therefore, you put nice topology that guarantees this sum goes through. Okay, so and then you do this machinery, and then as soon as you start with the graph E, there is a very nice way to construct a graph groupoid. I'm not going to go through this. This would become a different subject. But then you have a graph groupoid. As soon as you plug this into this machinery, you should be able to prove that this also gives you Leavitt path algebra of E. And again, to me, they have different nature, because this is generators and relations. You are just working with this evaluation of groupoids. So to me, two different ways to define these. Okay. And then the game starts. Yeah.
Could you give an example of the topology on separate groupoid?
Okay, let me not go through this, because this is not I want to emphasize, right? But the groupoid has to be ample. Okay, so it's an ample groupoid. Okay, but I don't want to go through that. But the idea is that now, once you have these two different ways, you can describe. You want to start with the language of a graph. Here is the language of a algebra, and you wonder what sort of properties you put on a graph to get some nice properties on the Leavitt path algebra. And if you are working with this one, so groupoid, and then you have a language of groupoid, and then you have here again the algebra. And you wonder what sort of properties you have to put here so that you get a nice algebra with, again. And this is what I don't really understand, why these relations you put here is so nice, that oftentimes whatever adjective you put here, you get an if and only if relation. This is, I don't know why those relations are so nice. What if I put some other relations? I might not get oftentimes this if and only. Okay. Now, so two different ways to define this one here. Now, let me go and define this in a different way, or describe these algebras in a different way.
It's on the road.
Yes, here. All right. So starting with the Bergman's paper in 1974. So he started with the ring R, and I'm gonna not put all the assumptions. It has to be a K algebra. R is a K algebra, K is a commutative ring, but let me just start with this is just a ring. And when I say a free or a finitely generated 3R algebra, when I say finitely generated 3 algebra, all I mean is the whole space of this form. And when I say a finitely generated projective R module, this time it could be not the whole space, but a big chunk of it that I can compensate with another chunk, and I recover Rn. Okay, so this Rn is the whole space. This one could be this bit that I can compensate with the other bit and recover the whole thing. So this one, for me, is a finitely generated projective modulus. Okay, and then Bergman starts with two finitely generated projective modules. Over R. And then he describes, it's a constructive description. He gives you a ring S with this map. Okay, so then S becomes an R ring. So this is a homomorphism. Now, such that if you lift P and Q over S, so now, and I'm now writing as left modules. In his paper, he's working with right modules, but let me just do left module. So you have this P and Q over R. When I lift this, they become isomorphic. So that's already very interesting because P and Q could be they have different structures, but there is an S that I lifted up and they become isomorphic. And not only that, if you have another ring, such that over this ring, you can lift it up and they become isomorphic, then it has to factor through S. So that means if you are here, you lift and you get isomorphic in here, already that P and Q goes through S, they are isomorphic already on this level, and then you go up, of course, you get an isomorphism on this level. So this is, I don't know, well, this is a universal construction
So
kind of.
you do not start with a module of homomorphism and then invert it,
No.
but you create.
Yes. This is the difference. That was known.
Yeah, the localization, con-localization.
Yes, that was already known, that if you have P and Q, a map between them, then I can convert that. But here, P and Q are just loosely sitting somewhere. Yeah. But he gets there also. His machinery also works if I give you P and Q with a map, I can invert that and it matches the previous constructions.
But if the modules were isomorphic already,
Yeah,
this is a new isomer.
that's correct. I'll get there. Yes, it's not that it gives you S is the same as R. When you plug that into the machinery, you get a new S. You'll see in a second. Okay, so all right. So again, you start with the R, you give me P and Q, I give you an S, which on the level of S, these two becomes the same. And then example, and he actually have this example. He has these examples. So K is a field, and he says, look, I give you K and I give you Kn. So these are finally generated projective modules, and then find the S. Let me just put a notation for S. One notation he uses is S is R P bar, meaning this bit is isomorphic to Q bar. So this is one notation. If you have a better one, let me know. So this is what he says. We are going to denote that S. Now, here, I give you K field, K and N, put it into the machinery. The machinery is constructive. So what you get, yeah.
The factoring morphism is a unique.
Yeah, there is a unique, yes. There is a unique isomorphism here. So therefore, this S is unique.
A unique that maps the iso over S to the iso over T.
Correct. There's a unique isomorphism with that property. Okay. So now, if I give you K field and then these two with his language, I want this to happen. And he recognized this becomes exactly that Ln. Okay, so this is another way to describe Leavitt path algebras. I did it with generators relations. I did it with groupoids. Now I'm going and saying that a ring which K would be the same as Kn. And of course, if I call this A and plug in here, or maybe, yeah, A, then I get A tensor K over K is isomorphic to A tensor Kn over K. And this is A, this is An. So without giving you those maps, I already recovered Leavitt's theorem. Okay, one more example. Again, noted in his paper. Again, K is a field. Now this time you get Kn and Km. You put into that machinery. This is LNM, already defined by Leavitt. And this means this time it's a free algebra with a lot of symbols. So I between 1 and n, j between 1 and m. And then you look at an n by n matrix of xij, just arrange them, or m by n, some n by m, and then arrange the other one by m by n. You force this to be 1, and swap the position, and you get the same thing.
Now, one question that comes to mind, and that these examples seem to confirm. I mean, so you have to finally design the projective. Okay? So you may think, so they come from idempotence. From idempotent matrices coming from such decomposition as we know there. Oh, now, so now you have two idempotents.
Yes.
And you want to make them more normal and equivalent.
Yes.
So you formally add the variables so that they become formally.
Yes.
Is that the process?
That's one way he goes through that, yeah. And that's exactly the next step I want to define Bergman algebras. And in his paper, he's talking about this, right? Yeah, and when I give you P and Q and I say, look at this ring, you have no imagination because, I mean, what is this ring? But we want to now define Bergman algebras with generators and relation, and exactly what you said I'm going to do. I'm going to convert this to idempotence and say, this is the ring with generators and relations. That's exactly.
It's a question by Dean Abrams saying, does Bergman's result guarantee that A is not isomorphic to AI or I?
Right. Okay. Good question. At this moment, let me think. At this moment, it doesn't guarantee, but the next step that he defined, he calculated its monoid. It shows that A is not isomorphic with A2. It has to go all the way to AN that becomes isomorphic. So when I define he calculates the monoid, there it's clear. But at this moment, you're right. I don't see a way to, yeah. The answer is that if I go next step in his paper and he calculates the monoid, you see that exactly there, A is not isomorphic to A2, A3, it has to be AN. Yeah. Yeah, that's a good question, though. And then what last example maybe is the one that really asks. So if you have K and I give you K and K, okay, say K is a field. These are two projective modules. And I say, can you now lift this so that you have a ring S? You lift this and they become isomorphic. So you have to put into the machinery of Bergman. I mean, if you show me, I say, oh, already it's K because K is isomorphic to K. But then if you plug into the machinery of Bergman, in order to get this universality, you see that this becomes K X inverse. So this Laurent polynomial is the answer. Okay. Right. So in order to get this one here, so he has to do a bit of work to get this ring S. So in the middle, he has two more theorems. Maybe I just put it here. Theorem 1 is that if you give me P and Q, finitely generated projective, then he constructs a ring S such that over this S, you have a universal map. So when you lift these, then you can define a map from P bar to Q bar. So that's one thing he defines. Theorem 2, if you give me a map over R, then you have another ring. You can lift this such that over this ring, this vanishes. So over R, you have this map from P to Q. It could be a non-zero map, but you would be able universally construct a ring S such that when you tensor these both, F becomes 0. Again, universally, I mean that if there is another T that does that, it has to factor through S. Okay, so he establishes these two, and then from these, he constructs that one. So see, you need to do a bit of work to get into this one here. Okay, now I'm going to define Bergman algebras. And what we did, we just went through the proofs. And basically what Willie said, we understood how these projections work. Because if I just give you a P and Q and say, oh, this is the ring, there is no way you can imagine what this ring is, right? Or this one or that one. But here is the Bergman algebras. Definition. Okay, R a unital K algebra. This K could be a commutative ring at the moment. At some stage when I want to move to calculate monoids and get into K theory, that has to be a field. Get E an idempotent, another idempotent. So you guess what I'm doing here. These are my interpretation of P and Q. And then get H, these symbols. Can I write here M times N? You understand that I goes up to M, J goes from here. And H star, another symbols. And then I defined a couple of Bergman algebras. Here is the first one. Bergman algebra 1 with the coefficients in a ring R attached to this E and F. Here it is. you get R and free unital ring R. So understand what this means. That means R with all these symbols, Hij, right? And the relations I put here is E, H, F is H. Okay, so remember A is this m by n matrix. H is an m by n matrix. F is an n by n matrix. So you put this here. This is your E. This is your H. This is your F. You multiply these. These are symbols. These are the actual elements of R. And you want to force this to be again H. So that gives you relations. Okay, so that's the first Bergman algebra. The second Bergman algebra is a quotient of this. So I get R, H, H star. Now I get involved these symbols.
But now it's not being picked up by the calculator.
Ah. So R, H, H star, and these two relations, E, H, F is H, F, H star, E. You see, I'm introducing some kind of involution here, H star. I think these are the one. And then you tell me if you have seen these kind of relations in other places. So B3 is R generated by Hij, H star Ji. And the relations, again, I'm going through the quotients. E, H, F is H, F, H star, E is H star, and H, H star is E. Okay, so this is a m by n matrix. This is an n by m matrix. I multiply these symbols, and I force that to be this idempotent. And then the last one, and this is the one that I want to work with because it has the best properties. And I just call it BR of EF. I could do 4, but okay, because this is the one I think. So it's R, H, H star with all of these plus H star, H is F. So E, H, F is H, F, H star, E is H star, H, H star is E, H star, H is F. So these are, we call Bergman algebras. And as you see, there is a morphism from B1 to B2 to B3 to B4. Okay, give some examples. What is the Bergman algebra? If I have to give you two identities. I put 1 and IN. Okay, and here I work with K. Okay. All right, so you see when I put 1 and IN, this becomes redundant because, 1 and I, it doesn't do anything. This doesn't do anything. It forces that H star be 1 and H star, H becomes IN. And that's exactly, okay, so that becomes, did I say, okay, B1. Okay, let me just do B1 first, B1 here. Then I have, this goes out, there is nothing here, and it becomes the free algebra generated by these H's, which becomes K x1 to xn. B2 1IN. Now I'm here. These goes out. I just end up with these generators. So I get K x1 to xn, x1 star to xn star. I do B3. Let me just put here, and then believe me, this gives you, I changed the place of E and F. Please do this. B3 is this one. That gives you the cone algebra. Yeah, associated to n loops. And then if I do B4, then I don't put the 4 here. B Y1 and IN. So this is this one, the one that I want to work. This gives you the Leavitt algebra LN. Okay. So it's enough to plug here some idempotence, and I put the easiest one, 1 and IN in here, and you see it exactly end up being the description of LN. And the game starts from here. Now study B, E, F for E and F. So can you describe, for example, when B, E, F is simple based on this E and F? Of course, when I put 1 and IN, I get a simple algebra. So can you come up with other idempotence properties that makes this simple? The other thing that I can do here is that, so this was the definition, but now my E and F is bunch of idempotence. So E and F is these pairs, and I just plug here. So for any of these pairs, I have H and H star. I keep adding more with these properties, right? And if I do it this way, I can describe Leavitt path algebras, because Leavitt path algebras are just a bunch of these.
I mean, if you say you have an inverse semigroup, and you start with a ring of its idempotent elements, then any other element is like an H. So I suppose that if you start with, you start with the K algebra generated by just elements, and formally attach an element H each time there is an X from idempotent P to idempotent Q, so that XX star is P and X star X is Q. So this will map to the semigroup algebra. The Bergman algebra will map to the semigroup algebra. And is this sometimes some
One more time. So one side you have semigroup semigroup algebra, right?
Yeah,
One side,
the inverse semigroup algebra.
One side. Okay. The other side you have.
Other side you have the Bergman algebra that you form by, for any element in the semigroup, each element of the semigroup X has an inverse, X star. And XX star is one idempotent, and X star X is another idempotent. Right? So for each X, you may add a formal thing that does that, exactly that, to the algebra generated by just the idempotence. Then you get an algebra which maps, I think, to the semigroup algebra.
Yeah. So
maybe that's
well, I have to think about. But you start with an inverse semigroup, right? It's an inverse semigroup. There are a lot of idempotence there. Then you get this, and then you want to see there is a Bergman algebra. With these
many E's and F's.
Yeah.
Coming from all the idempotence. You start with all the idempotence, and then you formally add the E's and the F's are all the idempotence in S. And then you formally add equivalencies between them, right? One for each element of S.
Yeah.
So you have a map in the direction, and maybe sometimes under some conditions that is nice.
Yeah, that well, I mean, if you do it this way, you can. I mean, this is just a construction of Bergman, but I just did it in terms of idempotence. So what you end up with is a hereditary algebra. So I don't know if all these inverse semigroups are hereditary. I don't know that.
So it's a hereditary, but that must depend on which R you start.
Yes. I start with K, a field. By the way, while we are here, if S is an inverse semigroup, this is a field. Is this IBN always? That's the question. Probably not, but while we are there. Okay, because if that's IBN, a lot of these are not IBN.
No, but you start with the semigroup associated to the graph, then there you get a conalgebra.
Conalgebras are IBN. And that's a paper of Gene. So I'm just asking in general, if you plug an inverse semigroup, is this one IBN always? Maybe not, but I'm just asking. Yeah.
There was a question in the chat saying if you consider the Bergman algebra for the M by N identity and N by N identity matrices, do you recover LMN?
Yes, that's exactly right.
Said that before.
Yes. So if I do B, I, N, I, M, then this gives me L and M. And again, here, all we did with Huanhuan and Raimund, we went through the proof and convert, as Willie said, projective modules to idempotence, chase the proofs, and these came out of it. So we didn't do that much here. Okay. The next step is, and this is the beautiful part of this paper, and so we are going to generalize this to graded versions. And this part, we had two choices. Either we go through another paper of Bergman that he talks about how to realize monoids, or we had to do a shortcut through smash products, because we are working with graded rings. We do smash product. We are in the usual ring. We could use Bergman's results, and that's what we did. So I think another way to do it is actually go through the whole paper of Bergman and just adopt to graded version. But okay, so
To do that, what you say, you need to adapt Bergman's to non-unital situation. Right?
I mean, you can keep. I mean, you can stay with Unital and then just work, or generalization to your. I mean, his papers are Unital.
Yeah, no, because I mean, the smash product will be non-unital.
Oh, yes. But the smash product is non-unital, but it's a direct limit of Unital. It's nicely behaved. So in each case, we just look at bits and pieces, and it goes through. Yeah. Okay. So monoid. So this is M, a monoid. So I think this is the kind of simplest structure in algebra, because you have just one addition. And then you want this to be a commutative. It has 0 and it's associative. So this is it. And I think in nature, you can come up with a lot of these monoids. I want my monoid to be conical, meaning that if you add 2 and you get 0, they have to be genuinely, both of them, 0. And I want here, I think this can be also relaxed, that M is finitely generated. That means generated by just a bunch of finite number of elements. This can be relaxed. And then the example is that, of course, if you have a ring R, then so to say, the non-stable K theory is this class of finitely generated projective modules over R, and this gives you a monoid with directs.
One be finite.
Projective over R. Say it again.
No. The piece, the monoid won't be finite.
M is, in principle, the monoids that I'm going to work with is finitely generated.
No, I mean V of R. Are you claiming that V of R is always finite if you have 80?
No. I'm just defining this.
Okay.
Yeah. But yeah, when I'm realizing M as a R, then that R has a good condition that this is finally generated. Yeah, but now in general, well, this is not the case. Yeah. Okay, now comes the Bergman theorem. So can I use another? With red is okay. Yeah. So theorem Bergman.
I think it is okay. I don't know if someone doesn't see it and say it.
Yeah. So M is commutative, conical, finitely generated, monoid. Okay. And then I get some I call it order unit. So what does that mean? That means that if you give me any M in M, you can compensate this M with some N, and you get some copies of I. Okay, so this means order unit. So this I, you can always, it's very, as you add it, like identity, keep adding it, it becomes very big. So for any M, there is an N that M plus M becomes Ki. So you fix that. And you always have an order unit if you have a finitely generated monoid, just get the sum of the generators. You always have order units, and you can have many different ones. So this is very sensitive here. Then Bergman says, exists a ring R. In fact, exists a K algebra, and K is that field, such that you have an isomorphism here, R goes to I.
People won't be able to see it. I can barely
No.
see it.
Let me see. Bravo. There is a ring R such that V of R is isomorphic to M. This R goes to I. So first of all, that, and this R is very special. Namely, if you give me another ring, and you give me an isomorphism here, so you realize M now with another ring, okay? Then the same story, then you have a homomorphism such that I know there is an isomorphism here to VR. And from VR, you can go to here with tensor product. Maybe I should do it this way if I'm doing left modules. And this becomes commutative. So for any other ring S, I have to give you some kind, because we went through this proof a couple of times, like maybe 5, 6, 7 times. And then next time I understood we missed a lot of the things. Maybe I'm still missing, but let me just give you some. So anyhow, one more time. So you start with the conical finite generated monoid. It's guaranteed there is a ring R which realizes M, and R goes to I. If you have another ring S which realizes M, and again,
you need
S goes to I.
you need the map for M to be S to be an iso, or just the homomorphism will do.
I think this is ISO. No, this is just a homomorphism. This is just a homomorphism, because this is homomorphism, right? So if you have another, if you have another, oops, that's a good question. Wait. Okay, if you have another ring S, such that you have, let me at the moment put it.
I mean, if you have it for an iso, you have it for a homomorphism.
Yeah, no, yeah. This is just a homomorphism at the moment. Let me just see. I have to look at the paper, but let me remember if I. So imagine you have a homomorphism from M to S, which sends I to S. Then it's guaranteed it factors through V of R this way. This is a homomorphism. Do I need a homomorphism or isomorphism? It's a homomorphism, I think. Do you have the Bergman's paper?
Maybe for
Not here.
one, maybe comes here, I don't know.
Oh,
I mean, we can think about the case in which
right.
you have one place to learn polynomials.
Okay, so now let me just stop here. Let me just explain. Yeah, I think this is how it should be homomorphic. I'm just trying to remember the proof. But okay, so a couple of things let me tell you here. First of all, maybe after I say this would become more clear. So this M is fixed. It's finitely generated monoid, okay? To me, this looks like ChatGPT. Each time it's constructive, right? But each time you click, you would get a different R, okay? So you give me this M, you click, it gives you an R with this isomorphism, and in this R can change depending on the relations and generators you pick here. And also, if you give me an S and I click, each time I might get a different homomorphism here, which makes this commutative. Now, this is theorem 6.2.
Yeah, I have 3 papers by Bergman.
This is universal construction in 1974.
So
Universal.
products,
Yeah.
some universal.
That's it. Look at theorem 6.2. Is it a homomorphism or isomorphism?
Theorem 6.
I have to think of the proof. It's a homomorphism.
For any algebra S and any homomorphism phi
Yeah.
of A being the monoid to the V.
Yeah. Good. So it has to be, it's a homomorphism. Okay. So here it is. It's a homomorphism. So that guarantees, I mean, in the proof, when you do this, that means this homomorphism gives you enough generators here, which are already satisfied by R. And then therefore you can push this R into S. Homomorphism is enough.
But understood this correctly, you're saying that there is an R which is constructive, but it's highly non-linear.
Yeah, because I mean, you start with this M and you have to pick up generators relation for M. You know, you can pick up different generators and relations. Each time you fix that, you get a different R, depending on generator relations. And then why is this now different? So you give me an S and this map here, I can pick up many different homomorphisms that this goes there. It's because if you give me this, okay, for each element M goes to some isomorphism classes, right? So then I pick one of them. It's up to me which one I pick. Depending which one I pick, I get a different homomorphism here.
So is R unique up to isomorphism or some notion?
No. R is not unique. R is not unique. Depending on what generators and relation I pick, R could be different.
Okay. But
Yeah.
we have some notion that makes them unique up to something, or
No, I don't think so. For example, R could be, in one way, R could be K, the other time R could be X inverse. Both of them works here, for example. Yeah. I can put more keep putting more generators. Both of these works. For example, M is Z. I can put here K, KXX inverse, 5 of them. So that's. Okay, so now let me just now.
Say for one thing.
Yeah.
Suppose the monoid
Is what?
free. So it's the natural numbers to some power. Natural numbers with 0.
Yeah.
Then, so
Then I can say
take n copies of the fit.
that's one of the examples of the, well, it could be one. Yes, I stop there.
Because, and then if you, so suppose now you have a course, right, of n to the m,
Mm.
right? So for each generator, you pick an idempotent, and then for each relation, you need to add a Moral for Neumann equivalent between the two, and this is, you do this, you add these variables, and is that it?
No, it's
Then
a
the
bit,
problem is when, how you prove that what you get at the end, I mean, you will, to force the relations is easy. The
Yes.
problem is to show that there are no more, than that you didn't get anything bigger than.
correct. But before that, I mean, if you give me a monoid M, okay, Bergman starts, so this is generated by X, Y, Z with some relations, right? So in order to recover this, Bergman starts with K.
Yeah.
So now here, the monoid V of K has just one generator. So he has to add more generators. So this is,
So you add an idempotent for each of X, Y, and Z.
but you have to do it in a nice way, because here he starts with M and then he gets one I in M, which X plus I is, or X plus some Y is Ni. So there are all these relations also come in. You have to take into account these relations. Okay.
Yeah, well, I mean, is this relation means there is an A and a B, such that A. The kind of, I mean, if you think of I mean, once you write R for the ring generated by three idempotents.
Mhm.
K has generated three idempotents, namely X, Y, and Z. Okay. And then so those relations are you can think of them as isomorphisms between some projective module
Yeah.
on this ring.
Yeah.
And then you apply the Bergman.
Yes,
Exactly.
you're right. So maybe there are more relations.
Yeah.
So he has two theorems. Let me put these two theorems here. And these theorems are proved in another paper, okay? So one is that, I mean, he uses technique. Okay, so I start with R, and I give you these P and Q, and I convert them, and this becomes S. Then he says that this monoid is the same as this monoid subject to these relations. So this is what you were asking. So I'm not adding more relations. So it's exactly VR subject to R equal to S. Okay, so he uses this. This is what you said here. I look at the relations and, well, I impose it here. But this is not enough. He has another one. Because if I give you M, he starts with K. This has only one generator. I want to keep adding generators till I hit those numbers. So this is the one that I really like. He says that if you have R, give me a projective module, any projective module. Then remember, there was a way to add a map, universal map between P to P. Okay, so that was one of then if you give me P and Q, I can give you a ring S, which give me a universal from here to here. Okay.
Isomorphism.
No, just a homomorphism. Okay, so
Yeah, that was stage 1 or 2 of your.
that was the one, stage 1. Okay. So now you give me P, which is a projective module. I construct this universal. And then remember, another one is that if you give me a map, I can extend that and kill it. Then he says, okay, I look at E2, and I'm going to say E2 minus E is 0. So I'm going to force this E to be an idempotent, okay? So this is a ring. And here is the punchline, that V of S is V of R, And remember, if this is an idempotent, then this P you can write as P1 plus P2. If you have an idempotent, okay. So you add two generators, one for P1, one P2, subject to P is X plus Y. This is brilliant. So you see, I could add more relation to what so if I start with K, okay, I can keep adding more relations until I arrive to the number here. But I have to control this one also. And this is where when I'm starting with M, artificially, I choose relations which imitate this kind of things. So this is his proof. So it's a bit, it's a bit tricky, but yeah.
And these results are in which paper?
These results, okay. These results in the same paper, but the main thing when working with monoid, he goes to another paper, which was also published in 1973. And this paper we did not understood, therefore we went through smash product. So there is a paper that he talks about the co-product of monoids. So that would be a very, very nice, maybe master thesis or PhD thesis to develop all of those in the graded setting.
Products of rings?
I think that one, because there he talks about the co-product of rings and calculate its monoid. But again, we didn't go through that. We just went through smash product. Okay, so now let me just tell you now what we did. How much time do I have? Not much.
1 minute.
I wanted to start our result now.
Okay, that's a good place to
Stop.
The lecture, yeah.
Okay.
After stating.
Okay. So then I would tell you the punchline. I would tell you the punchline. Here it is. So remember, Bergman starts with a ring R, P, and Q, finitely generated projective. And then he gives you this S.
It's unreadable, I think.
I need 5 minutes. Is that okay? Okay, so Bergman starts with this ring R, P and Q, finitely generated projective. And then it gives you this S. Okay. Over S, these are isomorphic. And he goes on and he shows that if you give me a monoid M, then there is a ring R which realizes that. Okay, so now our work starts from here, because remember we want to work with graded K theory because the group completion of this is K0 of R, and we are interested in that, but we are interested in the graded version. So we said, what if R is a graded ring? And now P and Q are graded finitely generated projective. Then you can imitate Bergman, but then you have to be very careful because here comes all kind of shifts, go back and forth. So then you have a graded ring S such that over these two graded finitely generated projective modules become isomorphic. Okay. Now, how about this? If you have a monoid, you can realize it as a usual ring. Now, if you have a monoid with an action of a group, so it's a gamma monoid, and I understand when you're working in dynamics, these come up, because now you have, this means a map from here to automorphisms of M, so you can keep moving things, so it becomes some sort of dynamic. So if you have a monoid with an action of a gamma, then you can find a ring which is gamma graded I cannot write on this one. Let me just try another one.
That's really.
So you have a gamma graded ring, which the VG of R realizes M. And of course, then the K0 of R, it's the completion of that. Okay? And let me just tell you, so Willie was saying, okay, look, I pick a monoid, Bergman gives me a ring, which realizes that. I put more structure of the monoid, for example, this gamma action. Now the ring becomes gamma graded. So put another structure. For example, if I want to get at the end, the one that Willie said, maybe V star of R. So this would be what? The projections?
Yeah.
Projections, yeah. So I define this. So I don't know what structure you have to put on M. We have to think about this. That when you realize it, you go through that via Bergman, that R maybe becomes a ring with involution. Such that then when R has a ring with involution, you're allowed to talk about this, and therefore you can realize this M. But then you have to put some structure on M.
The construction, Bergman's construction, you can do it just as you said. You start with a ring with involution, and then you have two projections, and then instead of adding an X and a Y such that X, Y is one and Y is the other one, you do exactly that, but you call
XX star.
yeah, why you call it X star and then you have a ring with involution.
Yeah, but I mean,
Probably not realizing the monoid, that's a.
but then I don't know. I mean, if I give you a monoid, Bergman gives you a ring R. It doesn't talk about involution. But maybe you say that I can come up with an involutory ring which realize any monoid M. I don't
know.
Yeah. Interesting. But I mean, I think the whole thing would be put extra structure of the monoid and wonder. Yeah, what kind of structure you would get on the level of a ring R? For example, here it has to be gamma graded. Okay, I'm gonna finish with one application we had, and here is a result of Guido and Leah. I just put it here very briefly. So we think that this is the complete invariant, VGR, or the graded grothendieck group is a complete invariant for Leavitt path algebra. So if that would be the case, then it has to capture a lot. And one of the questions was if this functor is actually full, namely, this was a conjecture 2 or something, conjecture 2, that if you have on the level of K0, or I can write on the level of monoid, if you have this monoid homomorphism which sends LE to LF, then can you lift it up to this? So that's on the way to prove the graded conjecture. So it has enough information there. So this was done by Guido and independently Leah, both 2023. And interestingly, yeah, for example, Guido's is that, okay, you can lift this and it becomes star homomorphism and it respects the diagonal, right? Yeah, and then in Leah's paper, she actually looked at infinite emitters also in there. Okay, so good. Now, with Bergman, in fact, we can show
was it between the monoids and the Bergman rings?
Yeah, no, not Bergman, any ring. So you could here have a graded any ring, any gamma or Z graded.
But still LE and not the Bergman ring.
No, this is it has to be LE. But here you don't have to have Leavitt path algebra for any ring that goes through.
Uh-huh.
So LE, I don't know how you can talk about this in categorical way. It's, yeah, LE is very universal, whatever. So yeah, so this would come out because we could develop Bergman's on the graded set.
And so you lift it to a grade algebra communication.
Yeah. And this again could be any Z graded ring.
Okay, is that?
Yeah, thank you very much.
So, one could ask, I mean, so on LE is the ring Bergman associates to ME, the monoid ME, or the M, so the talented monoid of E.
Yeah, Bergman doesn't, Pere, and yeah, they would realize it. Bergman just talks about,
No,
Yeah.
but the Bergman in your sense.
yeah,
Yeah, so say the talented monoid of E
can be realized, yes,
can be realized as the bigger of LE.
yes,
Now, say you have another monoid with an action of the integers. Then, by your construction, there is a ring whose bigger is that one.
correct.
Then you could ask whether this same question has also an affirmative answer for that ring. And have you thought of in those terms?
So you
Same question
pick,
without the girl. Maybe Bergman thought of that. I mean, so forget about the grading. You have a monoid that maps. You have a homomorphism between a monoid.
this works, yes. I mean, this result works without this, right? All of this works without this. I can just
but
forget the
without
grading.
any, I mean, I say you have a monoid M
Yeah,
mapping to V of some ring.
yes,
And now to this monoid M, you associate a ring.
yes.
Or Bergman does. So is it true that associates a ring R such that V of R is M?
Mhm.
So is it true that any homomorphism between M and V of S, say taking the fixed order unit to the order unit, lifts to a ring homomorphism from Bergman's R to this S?
Yeah, this is part of the Bergman, yes. It does. It does.
So it might make sense to ask whether the same thing is true in the graded world.
Right. It does make sense, but there is a little thing here. So let me just emphasize here why I'm working with GR and I'm not working with V, because when I'm working with V, and then VGR, you are not losing information.
What you are losing is ink.
Yes. Yes. So, when you're working with VLE, when you go up, you might get everything 0. So that means if you have a map from VLER to something else, that doesn't mean it lifts to the whole thing. You might lose a lot of information because it's not cancellative. But here, the beauty is that VGR is cancellative. So it sits here. So you are not, that's why this could be the functor for classification and this cannot be, because you're losing a lot of information. Yeah. So this might go to 0. Everything collapse to 0.
So are there questions from the audience?
Yeah, there was a question on the chat by Elia, where the map at the VGR level was order unit preserving.
This one has to be order unit preserving. So I start with the order unit preserving, and then I can lift it. Yes, it has to be order unit preserving because I'm using Bergman. Bergman wants this to happen. Yeah.
More questions?
I think if I just remove that, then I would be able to say LE goes to some graded Morita of A.
Some corner.
Some corner, something like that. And
Yeah,
that's what I don't want that.
Homomorphism, not
Yeah.
that proximity to itself.
Yeah, that's not pretty. Yeah.
More questions?
Now that I see.
Okay, if not, we thank the speaker again and end the.
Thank you.
So, Mr.